Hi there. Let's finish up the Power Models study guide. So, in the last video, we had determined that a power model is a good fit. Let's take a minute and review why that happens to be the case, and then we'll start here with question number 5, where we'll actually build that model. So, just to review, this is what we did. We verified that when we take the natural log of x and compare it to the natural log of y, if that is a straight line relationship, then that suggests that the power model is a good fit. So I just want to summarize that briefly. So the natural log of x, the explanatory variable, if we compare that to the natural log of y, the response variable, if that's straight, that suggests a power model. Y equals a times x to the power b. That is a power model. So, on the other side, what we verified doesn't work in this case if plain x compared to the natural log of y. So if the plain explanatory variable compared to the natural log of the response variable, if that plot is linear, that suggests that an exponential model would be a good fit. So again, like in the last video, notice the difference between these two is the role of x and b. Here the explanatory variable is the exponent. Here the constant b is the exponent. So something to think about to keep these two straight. Plain x for exponential. So this is the strategy to test for an exponential model. Plain x for exponential. So if you were looking at the natural log of both the explanatory and the response variable, if that gives you the straight line relationship, that's the power model test. So that's fundamentally the most important idea that we're using here. So let's actually create then the power model. We need to run the linear regression because the natural log of x and the natural log of y gave us a straight line relationship. So we're going to go ahead and use option 8 to run a linear regression just as we would have in the previous unit. So again, remember the explanatory variable that we want to use is the natural log of x, that's in list 3. The response variable we want to use is the natural log of y, that's already in list 4, and then we'll be able to fill in our model. So let's go to the calculator and take a look. So I'm going to call up my command, stat button, calculate. I'm going to use option number 8. So list 3 is the natural log of x, that's our explanatory variable. List 4 is the natural log of y, that's the response variable. We'll go ahead and calculate this. So this is a linear model. The constant comes first here, that's 1.75 approximately. And the slope is b right here, that's call it 0.22. So and here's our value of r squared, it's 0.71. So back to the study guide here. The natural log of lifespan, that's the natural log of y, that is equal to 1.75, there's our constant, plus the slope of 0.22 times the explanatory variable, which is the natural log of weight in this case. The value of r squared is approximately 0.71. So the first thing we're going to do is interpret the value of r squared in context. So again, 6 things are required. The value of r squared indicates that, first the percentage, 71%, that's the first thing, of the variation, that's the second thing, in the natural log of lifespan, that's the third thing, is explained by the linear regression. So we are explaining, that's the fourth thing. We are giving the type of model here. We have used a linear model using these natural logarithms, and that linear regression was built with an explanatory variable of the natural log of weight. So there's the 6th idea that needs to be in there for r squared. 71% of the variation or the variability in the natural log of lifespan is explained by the linear regression on the natural log of weight. So next, let's set up a scatter plot with list 3, that's the natural log of x, that will be our x value, but then this time we're going to use the resid list that was automatically stored. We're going to make that our y list, and we'll zoom 9 this. Again, we want to look at this to see if our model here is a good fit. This is a residual plot, so I'm hoping to see a relatively scattered residual plot. Let's take a look. So on the calculator, second y equals, we'll go into plot number 1 again. I'll leave list 3 alone, that's the natural log of x. I'll press second and stat, that will take me to my different list options, and here it is. The resid list is automatically created by your calculator. We'll put that in, we'll zoom 9 it, and there we go. As residual plots go, that's pretty scattered. I see absolutely no pattern there regarding the errors that we have in this model. That model looks like a good fit. So we're ready to do question 8, where we're actually going to build this model. In question 9, we'll look at how well it fits the original data, and then in question 10, we'll make a prediction with it. So here we go. Question number 8. So what we need to do to build the original power model, here it is. It should have a constant times x to the power b. The first thing we need to do is find the value of a. So notice, if I go back to the front side, this is the model that we were working with. Our response variable, the natural log of y, should equal this constant plus the slope times the natural log of x, the natural log of our explanatory variable. So the constant is the natural log of a. So our constant in the linear regression was the 1.75. So the equation that I need to solve then to find a, I need to take my constant, 1.75, and I need to set that equal to the natural log of a. So again, remember what a natural log is. That is a log base e. That's the natural number of a. So if I rewrite that in exponential form, what that tells me is if I take the base of e and I raise it to the power 1.75, that will give me the value of a. That's what I want to approximate here. We'll approximate that to 2 decimal places. So we'll go to our calculator here. So back from the home screen, second quit from the home screen, I'm going to press the second button and the log button, so that gives me e to the power, and I can enter the power I want. That's the 1.75. Press enter. So there's the actual constant that I want. We'll call it 5.75. Now, don't work too hard, because notice, I already know the value of b. I don't have to solve to get the value of b. It's right here. The value of b is the slope. It is the number that's multiplied to the natural log of my explanatory variable. We saw that on the front side. Look, here's the linear model. B is all by itself. It's not trapped inside of a natural logarithm. It's the coefficient in front of the natural log of the explanatory variable. So I've already got my value for b. It's 0.22. I don't have to do anything. That was convenient, so I'm ready to build the model. So my predicted y values are built by taking 5.75, there's my constant, times the explanatory variable's value to the power 0.22. That is the exponential model. So I can put that into the y equals menu, and we'll plot using the original data. The original data are in list 1 and list 2, and we can see using zoom 9 about how well we can see about how well this power model actually fits our data. So let's take a look. From the calculator, first of all, press the y equals menu. So we'll put in 5.75 times, and in parentheses, I'm going to put x, and then I'm going to raise it to the power. The power is 0.22. So if you're using an older style calculator, the power will be represented by a caret, and then after the caret, that's this symbol right here. After the caret, you'd put your 0.22. So let's make sure I've got my stat plot set up correctly then. I need to go into my plot number 1 and change it to be list 1 and list 2 so we can see this power model. There it is, list 1. And list 2 is the original data. That's what I wanted to model. We'll zoom 9 it. There we go. So hardly a perfect fit, but indeed this is certainly a better fit than a straight linear model. We knew that an exponential model wasn't a particularly good fit because when we transformed the data, we didn't get a straight line relationship. We got pretty much a straight line relationship when we were trying to test to see if the power model was a good fit. And it's pretty decent actually, so let's use it to make a prediction. So last question then. Question number 10, I don't know if you noticed or not, but in the actual data that you entered, if you look at the textbook data, the one mammal, well, there are many mammals that weren't included in the list data that you entered into the calculator, but in particular, humans were not included on this list. So the average human, according to our textbook, weighs 65 kilograms. So as a mammal, this model suggests that if I use 65 kilograms for the value of x, that we might be able to predict human lifespan using this model. So let's just substitute in our 65 and see what happens. So to actually do the prediction, my predicted y value would be 5.75 times the 65 kilograms to the power 0.22. So let's see what that suggests here. Back on the home screen, here's the 5.75 times the value of my explanatory variable, that is 65 to the power 0.22. So here's my prediction. We have a prediction that humans would live approximately 14.4 years. Now, of course, we know that the average human lifespan, although it varies from country to country, it's certainly more than 14.4 years. So humans are an example of an exception to this model, and we could think of many reasons why human beings would be exceptions to this type of a model. So the bottom line is, I would offer that human intelligence over the course of many thousands of years has helped us evolve to the point where we can extend our lifespan well into the 70s and 80s. Many people live well into their 90s and sometimes even past that. So this model is a good predictor for some mammals, but certainly not all. Human beings are an exception. So when you're making a prediction, it is a good idea to actually write out what you are predicting. And that actually makes me, when question number 8, I'm looking back at question number 8, something that maybe it would be a good idea to be a little bit more careful with here when I'm actually writing out the model. And we did this on our last test. So I did put the hat on my explanatory variable. Here is the response variable. But when you write out the model, you should always include, I'm sorry, I didn't leave a lot of space to do this. You should always include what the values of x and y represent. So in this context, x represents weight in kilograms. That would be a good idea to include. And in this case, I've already got the hat on my y suggesting that this model is going to make predicted or estimated y values, but the y's in and of themselves represent lifespan in years. So bottom line then, in addition to the linear models that we studied in the previous unit, the two curvilinear models that you will want to be familiar with involve exponential models and power models. And in particular, as I summarized at the beginning of this video, here is the test for seeing if data follow an exponential model. We can see if x and the natural log of y when compared to one another, see if that data is straight. That would suggest an exponential model is a good fit. Otherwise, as we saw in this example, if we look at the natural log of both the explanatory and the response variable, if that gives us a straight line relationship, then that suggests that a power model is a good fit. Hope this has been helpful.